My name is Patrick. I'm with PG Lifelink. We manufacture these panels. They're isolated power panels. What they're actually isolated from would be ground. We do that with a special transformer, really. And I'll get into that a little bit later. We first started using isolated power in the 70s. We had more medical gases being introduced in our ORs, more oxygen, more flammable gases, and some equipment shorts and sparks were causing explosions and fires. So that was its original purpose, was to reduce those shorts and sparks for the fires. We still use it today because of the amount of electrical equipment we have in the OR. It's a safety feature that if something were to be shorted with a ground fault, that would be either line, hot or neutral, shorted to ground, then the circuit won't trip, your breaker won't trip if that sure were to happen. And also there won't be a dangerous short, a dangerous spark. So those are two main functions of our panel here. Basic physical breakdown of the panel. We have the outside 480 volts coming in through our main breaker, up to our main breaker to the isolated transformer. That steps down the 480 to 120 isolated. We actually have 60 volts about on each line to ground in phase, added together, 120 phase to phase. From there we go down to our breaker and then out to the receptacles and the boom equipment in the room. This here is our LIM, line isolation monitor. What this is doing is measuring line-to-line voltage and also measuring line-to-ground impedance. And with that, it can do a calculation of, just using Ohm's law, of how much current we have going through ground. That's exactly what we're monitoring here. Right now, we don't have anything powered by a system. We have 0.39 milliamps in ground. It's a nice low number. What that means is if something were to be shorted through ground, that's how much current is going to be flowing through that system. This is important because medical professionals say anything above 5 milliamps can be harmful. Anything above 6 milliamps directly across the heart can be lethal. So we keep a nice close eye on this. It's going to alarm at 4.8 milliamps. You can actually test this yourself, which is required by code to do it once a year. Fairly simple. All you have to do is hold this push to test button. You'll see that current go up. We'll get an alarm at 4.8. That green safe LED is going to go off. The red one's going to come on. Go ahead and tap silence where you got that button pushed in. You'll see the safe go off, the alarm went off, and our silence light goes on.
And it doesn't register anywhere else, just here?
One sentence ahead of me. The only thing that this is hooked up to also, there's a remote board a few hallways down by the nurse station. It has a little remote that matches pretty much this, just with the 3 lights and the silence button. It will also alarm there.
With a room number probably, right?
It's got, yeah, we got the panel numbers on it right now. I'm not sure how the room number is going to work out.
Okay.
Yeah, good question. This is your maintenance logbook. You guys are going to keep this here.
Now you say only once a year. We do it once a month.
Once a month is required for the analog meters. The digital meters self-test themselves every 24 hours. And because of that, you only have to test it once a year. The first page here is just for me. I'll get one of you guys to fill it out. We have some basic definitions here. Normal mode, alarm mode, test mode. I don't know if you noticed, after we do that self-test, it actually goes through that calibration process automatically. It takes about 45 seconds or so, and then it'll come back up with a reading just like that. The system won't see it any differently. It won't stop any power. It's pretty much invisible. Here's a LIM wiring diagram. Could be handy if you needed help with those remotes over there. We have 3 wires running all the way back to that remote board at that nurse station. Here is that annual test. Pretty simple. Written it down in case you guys need it. And here's where you can record your test. This portion here would be the part that's required by code. Just holding that test button, watching the lights move the way they should. And this part is what we recommend as a manufacturer. Sort of what I'm doing today. We look at leakage current. We look at where our LIM is alarming. We also look at ground integrities, things like that.
Now, when we test our other ones, we test them with all the circuits on, then we test them with the circuits off. Is that gonna happen here too?
You can do that. That's a good idea. What you're actually doing is getting a kind of a source feed kind of, you get a look at what that's like when you turn all those circuits off, seeing if we have any sort of noise coming from our primary feed. That's what you're looking at essentially.
Okay.
So yeah, I'd say it's still important.
So if I had a high milliamp number, I should be able to shut those breakers, and when I shut the breaker that's causing the line that's causing the problem, I should see that number go down?
Exactly. Circuit 1 here, we got that clock on. It's over there. It's drawing some current. You can see it goes up quite a bit due to that clock.
So that clock's got some leakage.
Yes. It could be that, or it has digital circuitry, maybe a transformer, digital, DC transformer in there that's causing some leakage. Yeah. And then in the back here, we just have some product information. Curious to see what all we do, what all kind of panels you guys can get. Let's go in the room here for a little bit, and I'll give you a little demonstration.
So these,
So this is just a short from hot to ground. Notice when I plugged it in, we didn't trip a breaker. All we're getting is that alarm. What that means is, usually you can identify it by the first or the last thing you plugged in. You take it out, it's going to go off. Like you were saying before, if you don't know what it is, you can try flipping off individual breakers and isolating it that way. The procedure is if they can't turn off that alarm immediately, to get the patient to a safe state and then move him or her out of the room and then identify the problem more thoroughly. So what our transformer is actually doing, it has that high impedance back to ground, the isolated from ground. So if anything were to get shorted through ground, that impedance is going to add in series to whatever is being shorted. So we take that high impedance, add it to my low impedance, and I'm technically getting electrocuted now, but with whatever the monitor is reading. So let me take a look.
2.9?
2.9. So I got 2.9 milliamps going through me. I can't really feel anything, not even a tingle. And that's kind of the purpose for the system here. I'm okay. We didn't trip a breaker. We still have all of our important medical equipment working. So now we got any questions?
so the only way you would ever see that arc is if you went line up, if you went line to neutral.
Yes, if I went hot to hot, we're still going to get 120 right across this. If you find a way to get around it, let me know.